Okay. So here is our situation over finite fields. Now I'll just do my little example again. I have FP down here. I have, well, I can be a little taller. FP to the 6th, and I take some element sigma in this Galois group, maybe the Frobenius to the 4th as an example. And then, and sorry, to be clear, right, this is the Frobenius to the 6th restricted to FP6 to the 4th. And then I'm able to extend it to the algebraic closure easily in this situation by just saying be the Frobenius to the 4th, the Frobenius when I think of it like in the big extension instead of thinking about it in the little extension. And then this sigma tilde has some fixed field. And on this fixed field, right, which in this particular situation is Fp to the 4th, sigma tilde is the Frobenius of that field. And what is more, when I do this judgment map for my Galois automorphisms, asking them what power of Frobenius they are, right? This sigma tilde, oh no, that was too tall, goes to 4, right? Because it's the 4th power of Frobenius. And 4 is also the degree of this extension. Okay, this 4 and this 4 are the same 4. Now things over QP are more complicated. We still have a judgment map All right, so this one was an isomorphism. This one is just a surjection. But it still kind of judges like what power Frobenius each element is, right? And really what it does is like it looks, you know, so imagine for concreteness, an element of the Galois group that comes from some finite extension, right? And then you think of, you restrict it to an unramified extension, and then it really is a power of Frobenius, and that's like the grade you give this Galois element, right? So that's like this map. And what we're saying is that if we have an element sigma, so K here is a Galois extension. We have to start with a Galois extension. Like if you didn't have a Galois extension, pass to the Galois closure, right? Like, I mean, this is about Galois groups. So if you don't have a Galois extension, I don't know what you're doing here, right? You want that, okay? And so for like a not, so, you know, the situation here I think is like simple enough that if you know about these fields, you're okay with it. But this is a theorem, right, that you can pass to the maximal unramified extension of K and find some Galois element tilde sigma, sigma tilde, okay, and it's not necessarily like a power of Frobenius, right? But its grade is some integer, some positive integer. So that's like the kind of the equivalent of that, of saying like it's, you know, because the thing is that in this large extension, right, there are numbers that are not like an integer power of Frobenius, right? There's other elements. In the first lecture, I gave like a way with like some ANs to, you know, get compatible powers, right? So like, I mean, this is a big deal that you can get it to be an integer power and not kind of like a z hat power. And then this sigma tilde has some fixed field. Of sigma tilde. And it is the Frobenius of, I mean, there's not a Frobenius in that extension because it might not be unramified, but when you compute its score relative to capital sigma, it's 1, right? Which is like how you kind of say something is like the Frobenius, it's like a generator, right? So like relative to QP, you know, it was not a Frobenius, but you pass to some fixed field and then it is. Kind of how, you know, when you think of raising to the p to the fourth, that doesn't generate this Galois group, but when you pass to some extension, it does, right? So you know, like when you think of sigma as kind of the floor, then like it is. And then also, this n here, right, like the grade that sigma tilde originally had is not the degree of this extension, but it's the kind of degree of the unramified part of the extension, right? So here, this 4 agreed with that 4 because every extension's unramified, so that was the full degree of the extension. But here, you know, it's just kind of the unramified part of the degree, or the degree of the residue field extension from QP to sigma, if you will. Yep.
Okay, so really the issue with saying it's not just a power of the Frobenius is coming from the fact that this has non-trivial kernel, right? Do you have an example of an element, or like the idea of what the elements look like in the trivial that aren't like 0, or that aren't the identity?
Oh, yes.
What are the non-trivial?
Yes. So we can do a little detour. So I for inertia, the kernel of D is the Galois group of, and I just want to make sure I get that right, because I get sometimes a little confused with things. Yep, of QP bar over QP tilde. So they fix the maximal unramified extension and only play on kind of the ramified part of things.
Okay, so it's like whatever our like detector function D is not looking at anything that's happening in the ramified part.
Exactly.
It's like if you're doing anything in the ramified part, I don't care.
Yeah.
I'm just gonna neglect it and act to see what you're doing on the.
Exactly. Yeah.
And then it's a power for Frobenius under that restriction.
Yeah, because if your extension is unramified, then it's cyclic. It just looks like the extension on residue fields. So you're like doing finite Galois theory. So if you forget about the ramification, then you're exactly kind of in this situation, and then you have a Frobenius, a power of Frobenius. So this map D is like a way to get back, to forget the ramification, to get yourself in the good situation. Okay. So, whenever you have a Galois extension, an element of the Galois group, there's a way to think of it as the Frobenius of some extension, sigma, and the grade that you give to that, the associated automorphism, is the residue field extension of that field sigma. And I really like, just think of, it's a way to judge sigma, like to give it a value, like a size. All right. So now we're going to stop talking about that for a little bit. I want to talk about a finite Galois extension, right? So now we're firmly in the Galois world of K over QP. And I said this a little bit, right? So the ring of integers in ZP has a unique non-zero prime ideal. And the ring of integers of K also, right? And if I take the ideal generated by P in OK, that's some power of this prime ideal upstairs in OK. And one like really amazing thing when you have a DVR, which you do in this case, is that it's a PID. So this prime ideal can be generated by one element, which I will call pi because it's like a prime in this field K, right? So pi K is a prime in K. So it's kind of like P or minus P, right? I mean, like they're OK might have more units or whatever, right? But like you just pick one of them. And if you have an element of the Galois group of K over QP, it has to fix the prime ideal. So if you take like a prime element, it has to send it to some unit times that prime element. Like there's, it's not going to go anywhere wild. Like it's just going to multiply that prime by some unit. If anything, right? I mean, that unit could be 1. Let's take this with us. Okay. So it's also a fact that every element in the field K is of the form a unit times the prime to the m, where here V is a unit in OK cross. And what you should be thinking here, right, is that if you have a little element in QP, you can write it as some, power series. Actually, I is equal to n to infinity, ai, p to the I, right? And what I'm thinking here is that whatever power of p, right, the smallest one, I can pull it out, and then that will start, like an plus, and now math is hard, an plus 1, p, and so on, right? So like wherever the p's start, positive or negative, once I pull that one out, I have an element in not only in ZP, right? But also I'm assuming, you know, that, okay, that AN is not 0, right? So this is actually in ZP cross. This is a unit in ZP. So that's all I'm saying is like I can kind of like pull the P out and then have a unit. And the same thing happens over any extension. Yeah? Yeah. Okay. And I don't want to belabor this point too much, but there is like a valuation relative to the prime P in K, right? And for this X, you know, you count how many powers of the prime divide this number. So this valuation would be like that number M, right? Like the exact power of the prime that divides your number X. So here, like in this example, N would be the valuation of X. Okay. So what I want to do is define a norm map. Okay, so for little x and k, define the norm from k to qp of x to be the usual norm. If you've seen the norm before, which I think happened in Keith's class, you just, you know, I'm assuming k is Galois. You don't actually need for k to be Galois, but it just makes it easier, right? And you multiply all the Galois conjugates of that element x together. And if x is v pi k to the m, each of these elements respects multiplication. So the norm of x is going to be the norm of that unit v times the norm of this prime pi k to the m. Oh yeah, and how, sorry, now I'm looking at my notes, and how do I get this to be raised to the degree of k over qp? Oh yeah, sorry. So this is a product, right? Each of these sigma pi k is some like unit pi k, right? So this is going to be like for each element of k over qp, I'm going to get a little unit. So I'm going to get like a product of units, and then pi k to the m to the degree of the extension. Okay, so this is the norm of that unit, and then like the product of like the unit coming from like calculating things, and it's actually to the m, I guess, right? And then pi k to the m to the k qp. Okay, we're going somewhere with this. And now I'm going to use that k over qp is fk times ek, and that all of this is a unit to say that the valuation of this norm, right? So this norm element belongs to QP. Okay, you can see that if you act by Galois, it's fixed, so it has to be, it's fixed by every element of Galois, so it has to be in QP. Okay, and So if you want to see like how many powers of P divide this expression, well, this is all a unit, so like no powers of P divides it, right? And here you have pi k to the m fk ek, and P was pi k to the ek, right? Like that's how you can, that's one way you can define this ek. So, sorry? Yeah, so I'm just like, this is just that here. I was just rewriting this. And now I'm going to take the valuation. Right? So the valuation of this whole thing, because the valuation of the unit is 0, but, you know, the p-adic with this p, right? So like this is like 1p is going to be mf. Okay, so the valuation of this turns out to be the same as the valuation of pi k to the m ek fk, right? Because I forgot about the units, and that's the valuation of p to the m fk, because pi to the e is p, so I just put that together. And so that's m times fk, right? What power of p is p to the m times fk? It's m times fk, right? And m was the valuation of x. So what I get in the end is that the p-adic valuation of the norm of x is fk times the original valuation of my number x.
Can you go back to the last slide? How did you show that was?
I did not show it,
Oh, okay.
and I won't.
But it's not trivial, right?
Well, I think in this case, it's not hard to show, because if you sent a unit to something divisible by the prime, then you wouldn't be able to fix that prime ideal, right? Like if you took like the inverse Galois element, it would take the prime to a unit, so it would move outside of the prime ideal. So it's, you know, it's not like the kind of worst thing. Okay, and now if I apply this, which I guess I could have done, right, to the prime of my, or a prime of my field, well, that prime is divisible by the prime once, so that's just fk. Okay. So now we have all the ingredients to state the reciprocity map. Okay. So there are some hypotheses which I will come back to. But what I want is a map from the Galois group of K over QP to K cross, and it's actually, QP cross. And it's actually only going to be defined up to the norm of the non-zero elements of K cross. And so if I have a Galois element here, I have a way to create like my little sigma tilde, and the grade that I assign to this sigma tilde is the residue field extension degree of some field capital sigma. Now, that residue field degree, right, this F sigma, that's also the norm from sigma over QP of the prime of that sigma. Yep.
The norms of K primes aren't, isn't this QP prime? Aren't just the units of QP?
No. Yeah, and in general, there's, yeah. Okay, so I have two things that I have like judged the same, and like the map is just to send one to the other. Okay, and mod this norm situation. Okay, I mean, I haven't given the hypotheses. They're satisfied in the case of QP, and this is a group homomorphism. That sends to every Galois element, every element of some Galois group, to some element of QP cross, which in some sense, right, has been judged. Sorry, here, I need to take the valuation, right? So like, this is how I grade Galois elements, and this is how I grade elements of QP cross, right? And I have like two things that I've given the same score to. And as it turns out, like, it's not just like, you know, one student has a 10 out of 10, one student has a 10 out of 10. Oh, they're the same, right? Like, it's like this, you can actually send them to each other, and there's like a whole map. And like, I'm not going to tell you why. Like, it's like pages and pages and pages of stuff. But like, I hope this like motivates you to read it. Like, that there's just like this like wonderful world of evaluating, right? Like evaluation, right? Like, you give value to the numbers, like how big or how good or how whatever, right? And it is just like amazing that, you know, actually you can send one to the other, and it's like an actual like homomorphism between them. So far, right, all we have is a group homomorphism between these two. Yep.
Sorry, I'm just trying to figure out what the norm is on K cross. Or is that the norm of the elements in K cross?
Yeah, it's the set of all the norms.
Okay, thank you.
Yeah. In K cross. Yeah. I will not tell you, I will tell you the hypotheses. Okay, what are the hypotheses? It's that for every finite, unramified extension L of K, extensions of QP, every unit in OK is the norm of a unit in OL, right? So there was this norm map, and I was like, oh, you take the norm of a unit and it gives you a unit. Like, that's actually like a key point that like has to be true, which is true for QP. But you have to make sure that it's true if you want to get a reciprocity map. And if a unit in OL has norm 1, then there is another unit in OL. So I need, if a unit U in OL has norm 1, then there's another unit V in OL such that U is, so in this case that'll be the Frobenius of V over V. So two Galois conjugates always have the same norm because, you know, if you take like the product of like acting by Galois up here and the product of acting by Galois up there, you get the same terms just in different order. So certainly a ratio like this has norm 1 because the top and the bottom have the same norm, right? But we have to assume that actually every unit of norm 1 is of this kind. So the existence of a reciprocity map, right, is about unramified extensions being like well behaved, like with respect to the norm on their units. Like every unit is a norm of a unit, and every unit of norm 1 is of this like specific kind. And if your field is like well behaved like this, then you get a reciprocity map. Now this map, I mean, is like nice, but you can make it even nicer with a reciprocity law. So under more hypotheses, this same reciprocity map okay, let me just go back one thing, right? So this is a group homomorphism from some group to some abelian group, because multiplication in QP is commutative. So certainly it descends to the abelianization of this group, right? Like the commutators of this group have to be in the kernel of the map. Like that's a group theory fact that you can think about. Okay, so I'm gonna, you know, kill what needs to be in the kernel of this map for sure, just by like abelianization facts. But then you get an isomorphism. From the abelianization of the group to this like set there. Oh yeah, thank you. I was looking at this one and I was like, I put the P. I'm good. And rather than tell you the hypotheses, which maybe I can do some other time, I will tell you a consequence is that it allows you to classify the abelian extensions of QP, right? So the reciprocity map only sees like a billion groups, right? So if you have, you know, some non-abelian extension and you look at the abelianization, the reciprocity map can only see kind of like the, you know, the group with the subgroup that has abelian Galois group. So it only allows you to classify abelian extensions of QP, but it does. It tells you that there is a one-to-one correspondence between the finite abelian extensions of QP and the open subgroups of finite index in QP cross. And the correspondence is given by sending K to its norm group. Like that. And it's not obvious, you know, how to go from the reciprocity law to classifying the abelian extensions. But, you know, I don't have time to tell you. And it's complicated. Like, it's not really something that I think you necessarily want to watch someone do so much as like take time to think about yourself. But I wanted to like connect it to like Kronecker-Weber, right? So let's take this over, and I will very briefly right. So if you want to know all the finite abelian extensions of QP, right, then you want to study the open subgroups of finite index in QP cross. And it's a fact, and I put it, I think, like as some exercise, and like so we can talk about it tonight, right? But every open subgroup of QP cross of finite index contains so like these are powers of P that are divisible by F, right? So like 1, P to the F, P to the 2F, P to the 3F, and so on, right? And then some higher unit group where this part is elements of the form 1 plus P to the N times B for B in ZP. Right, so these are the elements that are congruent to 1 mod P to the N. So they have 1 and then a bunch of nothing and then P to the N and then like some extra stuff. So it's an exercise that this is a ball around 1 in the topology that Lori defined this morning, right? So these are like open balls. And then if you want them to be a finite index, then you need to like kind of chop up your series, your P's. Okay. We're getting to it. We're getting to the good stuff, right? Well, it turns out that the norm group, if you take the P to the nth roots of unity, that's exactly this open group of finite index, open subgroup of finite index. And if you take the rth roots of unity, and this time r is relatively prime to p, those are exactly, and I like changed my notation. Okay, but I think I can do it. And f is the smallest positive integer such that p to the f is 1 mod r. So, and I have 5 minutes to bring this together, right? So if your open subgroup of finite index contains this norm group, that's the intersection of one of these and one of those. So it's the norm group of the compositum of these two fields. So it's like some cyclotomic field. And then there's a reverse inclusion situation, right? So your open subgroup, all right, so say you have IU open finite index, and it contains the norm group of some extension, QP, these are all QPs, of some cyclotomic field, right? Then this is the norm group of some field K by our correspondence, right? Every open subgroup of finite index is the norm group of some field. And this open subgroup of finite index contains this norm subgroup. So then by reversing the inclusion, it tells you that the field K is contained in this cyclotomic field. And you get the statement that every abelian extension of QP is contained in a cyclotomic extension of QP, right? That's given, you know, by checking what you can fit in there. So that's how you go, right, from rate my automorphisms, like using the D map, rate your elements of QP cross using the valuation, right? That's what we did. And we got a map assigning Galois elements to essentially elements of QP cross. I mean, like mod, you know, these norm groups. And then we're actually able to make it, pardon me, an isomorphism on the abelianization. So here, I mean, there's more hypotheses, but this is for all K over QP finite, that you get this like reciprocity isomorphism. And then using that, you get that the finite abelian extensions correspond to the open subgroups of finite index. And then you kind of go to town understanding these open subgroups of finite index. And it turns out that they all contain the norm group of cyclotomic fields. And so this tells you that every abelian extension is contained in a cyclotomic field in that way. Yep. Right, so this is like Kronecker-Weber over QP. So you can get Kronecker-Weber over Q from this, but I'm not gonna do it. Like it's so if you think of the ingredients that we needed, right? We needed like this D map and this valuation map. And that really relied on there being like a Frobenius and a prime, right? And them kind of corresponding to each other, right? Like this sigma is the Frobenius somewhere, and then you take the prime and the norm. But like over Q, there's not one prime, right? There's not a Frobenius, like there's none of that. So the Adels are a way to kind of like deal with all the primes at the same time. So everything is just like a lot more complicated, but not, you don't gain that much understanding of like what's really happening, right? So this is doing it kind of like one prime at a time, like, you know, just the one prime, the Frobenius, and then like global class field theory is like, well, you kind of do this for each prime of your field. And so you can use Kronecker-Weber for QP, right? And then kind of make, you know, complete, make the extension, and then take the compositum of them like over Q and ensure that your abelian extension was contained in there. I mean, like it's like a little delicate, but it's like the ingredients are here if you're only interested in like Q. But yeah, it's true. This is like Kronecker-Weber for QP, not for Q. And like, I don't think we call it Kronecker-Weber. I mean, it's just like, it's become the word we use for this. Okay, so that's the through lines of class field theory. Like you need a map D to judge your Galois elements, a map V to judge something, which next time I can tell you a little bit about, right? So the issue with Q, for example, right, is that we're not going to use K cross, right? We're not going to use QP cross. We need something more complicated there, the Adels, right? But so you need some valuation on there, some V there. And then you go to town, you get your reciprocity map, you get the isomorphism, and then you can get classification of extensions. I think that tomorrow I will maybe like very, very briefly like peel back the onion to like those are the ingredients that we used. We didn't use them, but that we would use to prove all of these results. And then I'm hoping to do a little bit of Kummer theory, which is like if you restrict your attention to like certain very specific kinds of extensions, you can say something really explicit about them, which is in the same kind of genre of ideas. All right, but that's all for now. I think we did enough today.